So everyone, my name is Naushirwan and you're watching the first lecture on radioactivity. Now, radioactivity in general is a chapter that a lot of kids find daunting or difficult in GCSE physics. But in actuality, there's a large section of it that's just a lot of learning that you think, just things that you need to learn by heart. And there's a small calculation section that's related to it. That is slightly the difficulty or the difficult part of this entire chapter. So in general, about I'd say 80% of this chapter is just, things that you just need to learn by heart. And I'll focus on all of these things. And I'll also definitely focus on the numerical section that is going to come a bit forward in these lectures. Now, our first lecture is on the structure of the atom. And this is sort of the baseline that we need to know before we move on to any other things related to this chapter. Now, in most lectures, you'll see that physics is mostly, or GCSE physics is mostly related to GCSE physics. But in this section over here, we're actually going to be taking a large piece of GCSE chemistry over here and seeing what the structure of the atom really is. So it's very similar to GCSE chemistry in this case. Now, starting out, our structure of the atom, what is an atom to begin with? Now, any single object that you can think of in your life, whether it's, let's say, the table that you're sitting on, sorry, the chair that you're sitting on, this piece of water bottle over here, anything is made up of small particles known as atoms. They're the smallest particle of any sort of element. And these atoms, they're made up of three primary components. Number one is your dense section in the middle of your atom. This is called the nucleus, as we already know. Now, this nucleus has two sections of the atom. Number one, it has your protons, and number two, it has your neutrons. And around it, you have these things called orbitals, these circles over here. Now, these circles have small particles, very, very small particles known as electrons. And what these electrons are doing is they're orbiting around this entire nucleus. So they're sort of going in circles around this entire nucleus over here. So you have electrons, you have protons, and you have neutrons. These are the three constituent parts of your atom. Let's look at these three parts in more depth. Now, firstly, you have your protons. And as the name sort of suggests, these are your positively charged particles inside the nucleus. These are small particles that simply have a positive charge on them. Neutrons have no charge on them. They have completely zero charges. And electrons, the ones that are spinning around the nucleus, these are negatively charged particles, and they're just completely moving around the nucleus. Now, the first important thing that you guys need to be knowing for this chapter is that the mass of your electrons is actually very, very less in comparison to the mass of a proton or a neutron. The masses of a proton and a neutron are roughly the same, so we sort of assume them to be the same mass. But the mass of electron is actually this amount over here. If you divide the mass of a proton by 1,876, you roughly get the mass of an electron. All right, so these were the three main sections of your atom. Now, there's some terminology that you guys need to be aware of for this chapter. And you have two numbers that you sort of need to be knowing. First is your Z, and it goes by multiple names. Now, in your exam, it can sort of look like an atomic number. They can call it a proton number, or they can call it a charge number. Whenever you see any of these names, or you see the symbol Z, you should be knowing that they're sort of referring to the number of protons inside of that element. So the number of protons inside that element is the atomic number, the proton number, or the charge number. And likewise, if it is a neutrally charged particle, this is to say that it has no sort of charge on it, the number of protons and the number of electrons are equal in that case. So by that logic, this proton number, this charge number, or this atomic number also gives you the number of electrons that are inside of that element. The second number that you need to be aware of is your mass number / atomic mass / nucleon number. Now, this is also given the symbol A, and this is just the total number of protons and neutrons inside of an atom. So if they tell you that this is the A number, this is your mass number, this is your atomic mass number, all of this stuff, you should be aware that they're referring to the total number of protons and neutrons inside of an atom. Okay, now this is the sort of notation that most elements are sort of represented by. Here is your X. This is any element. This can be anything. It can be carbon, it can be magnesium, it can be anything. On top, you have your mass number, which is your A, and on bottom, you have your proton number, which is your Z. A gives us the total number of protons and neutrons inside of this element, and Z simply gives us our proton number, or the number of protons inside of the element. Now, if we want to find the total number of neutrons inside of an element, all we're going to do is we're going to subtract the A value with the Z value, the mass number with the proton number to get the total number of neutrons inside of an element. Okay? Now, let's move on to perhaps the more important section of this chapter, and this is called isotopes. Now, isotopes is an atom whose proton number is the same to another element, but its nucleon is different. This is what we call an isotope. And on the right-hand side, we can see a few examples of hydrogen and its isotopes. So you have protium, you have deuterium, and you have tritium. Now, in most cases, in any of your chemistry classes, if you take chemistry, you would have dealt with protium, which is your proton and your electron. But in actuality, hydrogen can exist in two other forms, which are these two things. And you can see that the number of protons in all of these, right? Number of protons in protium, deuterium, and tritium are still one. So this has one proton, this has one proton, this is one proton. But the number of neutrons are actually different. So you can see deuterium has one and tritium has two. And hence, all these are just isotopes of the same element known as hydrogen, right? So when the number of neutrons sort of start to change between these three forms, their nucleon number as a result also starts to change. Their mass number starts to change. So while protium has one nucleon number, this will have two since it has one proton and one neutron. And likewise, this has three since it has one proton and two neutrons. So these are clear examples of isotopes. But why are isotopes actually very important? Now, why are isotopes important? Isotopes are really important when we're discussing the concept of radiation. Now, in actuality, when you're looking at these isotopes, let's take the example of hydrogen. In actuality, not all of these isotopes are going to be stable. Now, if we look at the example on this slide over here of lithium, lithium has three isotopes, just like hydrogen. Lithium has an Li7, an Li8, and an Li6 isotope. Now, while three of these isotopes actually exist, only one of them is a stable isotope. This is to say that one of them can only exist in sort of a stable state. That is my Li7 isotope over here. Now, both of these atoms, Li6 and Li8, they are currently unstable, and what they want is they want to mimic the stable isotope over here. They want to become an Li7 isotope. Now, if I wanted to convert my Li6 isotope to an Li7 isotope, what do I need to do? Well, we know the protons of every single isotope are the same. So there's a difference in their neutrons. Now, Li6 in this case wants to gain a neutron so that it becomes an Li7 isotope, right? Now, if we look at Li8, it wants to lose a neutron so that it becomes an Li7 isotope. Now, let's say there's a certain process, a process known as radiation, and if these isotopes undergo this process, they can become this Li7 isotope. They can become this stable isotope. So in actuality, when we're talking about radiation, radiation is simply a balancing act, a process through which unstable isotopes convert themselves into stable isotopes by doing something. Either it's gaining something, either it's losing something. In this case, what we're getting for Li6 is going to gain a neutron. This is its radiation, and it is going to become an Li7 isotope. Likewise, Li8 is going to emit a neutron, is going to sort of let go of a neutron so that it can become a stable Li7 isotope. All right? So radiation is simply the process in which unstable isotopes do something in order to become stable isotopes or stable atoms to begin with. Now, there are actually three types of radiation that you have. Number one is your alpha rays, you have beta rays, and you have gamma rays. We need to know the properties and their nature of all three of these radiations. Firstly, for alpha rays, by nature, they are helium nuclei. This is to say that they are simply we're referring to just the nucleus of your helium nuclei, and it has a +2 charge. Now, many of you are aware that helium is a noble gas. This is to say that it has no sort of charge on it. So how are we saying that helium has a plus 2 charge? In actuality, in this case, what we're talking about is just the nucleus of the helium atom, right? Now, if we talk about the nucleus of a helium atom, what it has two protons, these blue things, and I'm going to draw the neutrons with the red, right? So I have two neutrons and two protons. Now, if you look at these two examples, you have two protons over here with a positive charge, and neutrons, they don't have any charge. So I'm just going to draw a zero over here. Neutrons have no charge on them. So because of this reason, because of the fact that neutrons have no charge on them, and we're just looking at the nucleus, this entire nucleus is going to have a plus 2 charge. So that's why alpha rays, they have a plus 2 charge over here. Okay. Now you have a few properties that you need to be aware of for your exams. Firstly, alpha rays, they do not travel well in air. They cannot travel very far. This is to say that they can only travel only 2 centimeters inside of air, and they're very easily absorbed by a thin sheet of paper. Now, because of this property, alpha rays are just very, very bad at penetrating things. So if you talk about passing an alpha ray through any object, it will find it very difficult to pass through that object because it's just not one of its properties to be very penetrative. So it can simply be blocked by a very thin sheet of paper and it can only travel 2 centimeters in air before it is easily absorbed by even just the air molecules. Now, secondly, alpha rays have high ionization power. Now, what do I mean by ionization? Now, if you know from chemistry, ionization simply refers to creating an imbalance of charges within an element. So if I sort of increase the negative charge in an element, or if I sort of decrease the negative charge in an element, that creates an imbalance. So if I increase the negative charge in an element, let's say I give it an extra electron, it's going to have a negative charge on it. If I take an electron from that element, it's going to have a positive charge. So ionization is simply the process of doing that. Now, what do I mean by high ionization power? It means that alpha rays, when it collides with atoms of anything, let's say it's colliding with certain air. This is my alpha ray, the blue ray that I'm traveling over here, and it is colliding with a few air molecules over here. Now, alpha rays have this capability of making these particles ionized, creating an imbalance of charges within these atoms. So it is very good at knocking out the electrons from these atoms. So if these alpha rays collided with a few air molecules, it is going to knock out the electrons of these particles and leave a sort of charge on them, a charge imbalance on these atoms. That is what I mean when I refer to high ionization power of alpha rays. Okay, so they're very good at creating ions with any particle that they sort of collide with. Now, thirdly, your alpha rays, they deflect in a magnetic and electric field. This is to say that when you pass them through either an electric or either a magnetic field, you're going to see their pathway sort of start to deviate, start to change. Now, if you look at this example over here, this is passing it through an electric field over here. You have a negative node over here and a positive node over here. So your alpha particles are sort of traveling in this arc and they're shifting towards the negative side of the plate. The reason for this, it has a plus 2 charge. So obviously it will be attracted to the negative side of this plate over here. So that's why it deflects in this direction. Now, when we look at alpha rays inside of a magnetic field, this is a magnetic field. These crosses mean that your magnetic field is into the page. Now, when you pass the alpha ray through through this magnetic field, it is going to travel in this upwards arc over here. Now, the way that we found this path is using Fleming's left-hand rule. And you can do so yourself. If you recreate the Fleming's left-hand rule, you'll get your answer in this direction. So your thumb should point sort of upwards in this case. Let me know if you guys want a video on the Fleming's left-hand rule. Okay. The second type of radiation that we have is your beta rays. And by nature, these beta rays, they are simply just electron particles. So they're just a sort of name for a moving electron particle. Now, the properties that they have are as follows. Firstly, they have a single negative charge on them. So like how alpha particles had a +2 charge on them, this is just an electron, so it has a negative charge on it. Secondly, they have moderate ionization. So they're not as good as ionizing any sort of particles like the alpha rays. So they're not as good as that property that the alpha rays have. Now, thirdly, they are more penetrating than your alpha particles. So they can easily pass through paper, which alpha particles weren't able to do. And they are absorbed by 5 millimeters of aluminum sheet. So if I pass beta rays through 5 millimeters of aluminum sheet, they won't actually cross the other side. They'll simply be absorbed by that aluminum sheet. Now, clearly, this is more penetrating than your alpha rays over here. So they can travel further in air, your beta rays, and they can also pass through paper, which alpha rays couldn't do. Okay. Now, fourthly, these also deflect, beta rays also deflect when you pass them through a magnetic field or a electric field. So for the electric field, you can see this example below, the same example over here. Instead, you look at the green line over here, and it is attracted to the positive side over here because beta rays are a negatively charged particle. So they'll obviously be attracted to the positive side over here. Now, when you pass them through a magnetic field, you need to again apply Fleming's left-hand rule. The only change that you really need to make over here is the direction in which you're sort of pointing your middle finger, which denotes or which is supposed to refer to your current in the field. So for beta rays, since the beta ray is passing in this direction, you're going to take the current in the opposite direction. Because conventional current sort of flows opposite to the negative charge, right? Alpha rays were positive, that's why we took the same current direction as the path of the alpha ray. But for beta ray, since it's negatively charged, we take the current direction completely opposite. So beta rays, if they're traveling in this direction, you're going to take your current in the leftwards direction. All right? That's the only change you need to make. Besides that, the magnetic field in this example is completely the same. It's still into the page. All you need to do is adjust your current to go in the leftwards direction, since beta rays are negative charge and your conventional current travels from positive to negative. So that's why we sort of take the opposite direction when we're talking about any sort of negative charge. In this case, beta rays were negative, but if there was even a single negative charge in this case, you would do the same thing. You would take the current direction completely opposite. Okay, lastly, you have your gamma rays. And by nature, these are electromagnetic rays. So they are a part of the electromagnetic spectrum that you might have read in your waves chapter. Now, gamma rays, they are released when your nucleus has some extra energy that it wants to get rid of. So let's say it is sort of in a hyper state. It wants to release some energy that it has. So it lets go of gamma rays. Now, gamma decay often happens after the emission of alpha or beta particles. So after your alpha or beta particles have left a certain nucleus, you oftentimes also get some gamma rays leaving from them as well. Now, gamma rays, they have a few properties as well. Firstly, they have no charge on them. Since they're simply electromagnetic rays, they don't really have a charge on them. Secondly, they are very bad at ionizing things. They're very bad at ionizing particles. Thirdly, they are very, very penetrating. So if you compare the penetration of the other two particles to gamma rays, you'll see that gamma rays are extremely, extremely penetrating. They can very easily travel through air, something that alpha and beta particles both struggle with. They can easily travel through aluminum sheets, which beta particles were simply absorbed by a 5 millimeter aluminum sheet. Gamma rays can easily pass through that. And they are absorbed by 25 millimeter of lead. So if you have a 25 millimeter lead sheet, only then can you block gamma rays. This clearly is a much larger thickness than any of the other two rays that we've seen so far. And lastly, you need to remember that gamma rays, they simply pass by undeflected in both electric and magnetic fields. If you look at this example, the wave over here, gamma rays, the blue one, they're simply passing by undeflected. They're doing nothing. And they're also passing by undeflected in this case. All right? So these were the properties of these three types of radiations. Okay, now let's talk about decay. Now, decay is simply the process of emitting radiation. So if you're emitting any sort of radiation, we know three types of radiation right now: alpha, beta, and gamma. Any process that is involving a nucleus emitting these sort of radiation is called decay. Now, emission of radiation is a completely random process, and it is unaffected by any external factors. So there is nothing that we can do to sort of change the amount of decays that are happening in a certain amount in a certain time. So if there's a nucleus, we cannot really do anything to make it decay, or make it decay faster, make it decay slower. We cannot raise the temperature or increase the pressure. There's nothing that we can do to sort of change how many decays are happening in a certain sample there, or any sort of how quickly your entire sample is decaying. So it's a completely random process over here. So the first type of decay that we have is your alpha decays. Now, in alpha decays, the element's nucleon number decreases by 4 and the proton number decreases by 2. All in all, the element loses 2 protons and 2 electrons. Now, the reason that your, your proton number decreases by 2 and your nucleon number decreases by 4 is because let's look at the configuration of helium over here. Helium has 4 nucleon number, nucleon number, and 2 proton number. Now, if this entire particle is leaving a nucleus, so by that logic, it is going to lose 4 of this. It's going to lose 4 from its nucleon number and it's going to lose 2 from its proton number. So this is sort of a general formula that you have for any sort of alpha decay, right? And we can also look at the example over here. Now, you guys don't really need to know the element names after a certain decay. So like uranium is sort of being converted into thorium over here. You don't really need to know these because they'll already be giving you this. They'll already be giving you the names. You just need to be able to fill out these numbers over here. So in most questions, they're sort of going to leave this place empty and they'll just ask you to write what numbers do we have over here? What is the mass number over here? What is the proton number over here? So uranium-235 is undergoing helium decay, alpha decay. So it is going to lose 4 from its mass number. So it's going to be converted into 231. And the proton number is going to decrease by 2, since it is also losing 2 protons. So if you look at this, since this particle is leaving the uranium nucleus, it is also going to take 2 protons away from it. So that is why we're decreasing the proton number by 2. So all in all, in alpha decay, do remember this, that the element loses 2 protons and 2 electrons. Sorry, it's supposed to be neutrons over here. It's going to be neutrons. All right. So keep that in mind. All right. The second type of decay that we need to be knowing is your beta decay. Now, in beta decay, a neutron is simply converted into a proton. So the nucleon number stays the same, but the proton number actually increases by 1. Because, again, one neutron is being converted into a proton. So if you look at this example over here, this is sort of a general formula for your beta decay. You're going to increase the proton number by 1, and you're simply going to write the beta decay that is happening over here. All right. So this was beta decay. All you need to do is simply increase the atomic number or the proton number by 1 because one neutron is simply being converted into a proton. So the total number of neutrons inside of the element, they're going to decrease by 1, but the total number of protons inside the element, they're going to increase by 1. All right. Now, before I go on to the next slide, there's also one other trick that I want to sort of tell you guys to make sure you guys are getting the correct answer. And this is to simply add up all the numbers on both sides. Now, if you take a look at this example over here, we currently have in our left-hand side, before this arrow, we have 92 in our proton number. And over here, we have 90 and we have 2. If you add both of these numbers, basically the proton numbers on the right-hand side, they are supposed to equal the proton numbers on the left-hand side. So If you add 90 and 2, you're going to get 92. And that just tells us is that the numbers that we actually put in are correct. If we do the same thing with our mass numbers, you're going to get the same idea. On the left-hand side, we have 235. And on the right-hand side, if we add both of the mass numbers, 231 and 4, you're going to get 235. This is sort of a way to check your answer and to make sure that you actually put the correct numbers inside of this entire equation. So do make sure to check your answers whenever you can. All right. Now, in gamma decay, the atomic numbers and the nucleon numbers simply do not change because there's sort of nothing that's leaving the nucleus. So for gamma decays, this is the easiest one. Nothing really changes. So you just need to be aware of that. So this is it for the first lecture on radioactivity. I'll be uploading 2 more lectures, so do make sure to look at them. And that's it for today, guys. Allah Hafiz.